In this section, we're going to look at rate concentration graphs. So we've been measuring the effect of concentration on rate using our initial rates method. What if we had a lot of data? How could we look at a graph and tell us, use that graph to tell us the order of reaction? So rate concentration graph, when you get given a title of a graph like that, we know that the first thing mentioned is going to be on the y-axis. So we're going to write rate on the y-axis, and then rate is change of concentration per unit time. So the units of concentration per unit time, rate is in moles per decimetre cubed per second, and we're going to vary concentration of reactant A in moles per decimetre cubed. Now, if a reaction is zero order with respect to A, what that means is that changing the concentration of A has zero effect on the rate. Rate is independent of concentration of A. So we can write that, rate is independent of concentration of A. But what does that mean for the graph? It doesn't mean that there is no rate, it just means that the rate will not change when we change the concentration of A. So as we move along this x-axis, the concentration of A is changing, but the rate mustn't change. So we're looking for a straight line that is parallel to the x-axis. So not on the x-axis, but parallel to it. So it's the same value of rate at all values on the x-axis, at all concentrations. So we're looking for a straight line anywhere on the y-axis, a straight line across parallel to the x-axis. And that would show us that it was zero order with respect to the concentration of A. So we've got zero order, a straight line parallel to the x-axis. Now, if something is first order, and again, we're plotting a rate concentration graph. So remembering that rate is change in concentration per unit time. Concentration is in moles per decimetre cubed. Then in a rate equation, if it was an overall first order reaction, our rate equation would look like this. And so we can say that rate is directly proportional to the concentration of A, because K is a constant. And what does that graph look like? Well, that graph would look like a straight line, a y equals x line, a straight line through the origin. And it is important to say through the origin to distinguish it from our zero order. So it's still a straight line, but this time it's through the origin. And that would show us that our reaction was overall first order, a straight line through the origin. And then finally, if our reaction was second order, so rate, again, changing concentration per unit time against concentration, then we're looking at an equation that goes rate equals something like Ka squared. So we're saying that rate is going to be proportional to A squared. So if you think back to GCSE, we're looking for a y equals x squared shaped curve. And that is a parabola where if you double the concentration of A, then you're going to have a 2 squared effect on the rate. So it's going to go up 4 times. We've got the positive half of the y equals x squared parabola here. Okay, so we've got our 3 different orders and our 3 different shape graphs that we've got to be able to recognise.